Okay, so we're continuing with optimization. We're just going to kind of be building on the concepts that we learned on block day. These are going to be just a little bit more complicated. So, it says a farmer has 1,000 feet of fencing available. There is an existing fence that separates his land from his neighbor's. Using that fence and his 1,000 feet of fencing, he wants to create a maximum enclosed area for his animals. What should the dimensions of his enclosure be to maximize the area? So you want to go back, you want to read the problem once, then you want to go back and reread it again. We've got 1,000 feet of fencing. We have an existing fence. That's going to be used as one of the barriers. So I'm going to draw the existing fence right there. He's going to create a fence around that. So his fence is going to come out like this. This is his fencing in red. When people make fences, you know, like an enclosure, it's usually a rectangular shape, so that's implied. So he does not need to use fencing here, guys. He's using that one that's already there. So what if I call this X? What's this going to be if it's a rectangle? X. I'm going to call this Y for now. He has 1,000 feet of fencing. So what's the equation based off of these? 2x plus y has to equal 1,000. So therefore y is going to have to be 1,000 minus 2x. So we're going to call this 1,000 minus 2x. Anytime you choose to use a variable other than x, you're going to have to get rid of it. Now, the problem at the end says, what dimensions do we need? So he could have used like 100 feet here, 100 feet here, and that would leave him with 800 here. Okay, that would be one thing he could use. But we're trying to maximize the area. That's not going to maximize the area, 100, 100, 800. Maybe it's 200, 200, what, 600? Maybe that's it. That's what we're trying to figure out. The area now. Well, the area is going to be base times height, or length times width. What do I have to do with this area? Multiply it out to start with. 1,000x minus 2x squared. Now what? Take the derivative. That's going to be 1,000 minus 4x. What do we have to do now? What's the slope going to be? To have a max or min, the slope has to be 0. So I'm going to get 250. Now, just to double check and make sure that's going to maximize, I'm going to take the second derivative. The second derivative would be negative 4, which means it's concave down. If we're concave down, we have to have a max where the slope is 0. That's what we want. Maximize the area. I'm never going to ask you a question for a maximization of the area and then it ends up being a minimization for your answer. But that could happen. So that's why I just want you to see how you can check it. So this is now going to be 250. This is going to be 250. 1,000 minus 500 is 500. And so our dimensions are going to want to be 500 by 250. That's going to give us the maximum area. If we had been asked, what is that maximum area? Well, we just do that. So the maximum area we came up with was, they didn't even ask us this, but it's 125,000 square feet. Okay? So that beats the 100 by 800. That would only be 80,000 feet. So that's going to beat that one for sure. And it's going to beat any other one we can come up with. Any questions on that? All right, let's look at the second one. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with a maximum volume? Guys, this classroom is almost like the situation we're talking about. Just imagine this classroom without the ceiling. We have a square base here, pretty close to a square base. So the question is, if we have this square base, what should the dimensions be of the square base? And what should the height be if we have to have a surface area of 108? Let's draw a picture. So it's going to be something like this. This has to be x, this has to be x, because we have to have the square base. But we don't know how tall this box should be, so I'm going to have to call that y. I don't know what the height should be, and I don't know what the base should be. But I know it has to be a square base, so it's got to be x and x. What dimensions will produce a box with maximum volume? Okay, what's the volume then? If I do it in terms right here, what's the volume? Good, x squared y. I'm not allowed to use y though. So now I'm going to have to do something with this 108 in order to get rid of the y. Take it one step at a time. Here's the floor of our classroom. What's that area? X squared. Hold on. X squared plus, but it's the surface area of this whole thing with an open top. So what's the front wall? If it's x and y, what's that going to be? What's that area? Right here. This is our front wall. X and y. It would just be x, y, right? What about the side wall? What's its area? X, y, back wall. So what's the formula? X squared plus 4xy must equal 108. If we were counting the ceiling as part of the surface area, what would I have to do? I'd have to have 2x squared. I'm not allowed to have a y here, so I have to solve this for y and then plug it in here in order to not have the y. Solving this for y, I'm going to have 4xy equals 108 minus x squared. I have to divide this by 4x. So y is going to equal 10 divided by 4 is 2 with 2 left over. 28 divided by 4 is 7. So I get 27 over x. X squared over x is going to be x over 4. There's my y. This is not what I take the derivative of. I take the derivative of volume. So I have to go back up here to my volume, and I have to replace y with 27 over x minus x over 4. I'm going to multiply. I get 27x minus x cubed over 4. Taking the derivative of 27x is 27. 1/4 times 3 is 3/4 x squared. If we're maximizing or minimizing, what do we need the rate of change to be of the volume or the slope? What happens at a high point or low point? The slope is 0. So I set this equal to 0. To solve, I would bring this over here. So it's positive 3/4 x squared equals 27. How do we get rid of 3/4? Multiply by 4/3. Do it this way. 27 divided by 3 is 9 times 4. To solve for x, I take the square root of both sides. That's plus or minus 6, but I know I can't have a negative 6 as my dimension. Doesn't make sense. So now I know this has to be 6 and this has to be 6. But I still don't know the height. How am I going to find the height of the box? Good. I have to plug it back in here, don't I? So I have to do x squared is going to be 36 plus 4 times 6 is 24 at y has to equal 108. I had to plug it back in here to be able to find y. Solving this, I'm going to get 24y equals, if I subtract 36, I get 72. 72 divided by 24 is 3. And so the dimensions are going to have to be 6 by 6 by 3. That's going to be the box that's going to have this surface area and that's going to maximize the volume. And the reason you'd want to do this is because you're going to cut down on the cost of your boxes. Right? If you maximize your volume, you can stuff a bunch of things in there. Like if somebody's going to order, a ton of items, you can fill it up more and save cost on your cardboard to create that. Although, Amazon never does that, do they? Do you guys ever get stuff from Amazon? There'll be like 2 little things in this big, huge box. But if they had to do this, if they wanted to maximize their volume and keep the surface area constant, that'd be the way you do it. Okay, that is it. I want you guys to try those problems for homework.